Okay, so if you're an engineer, your whole world is built on logic, right? You design systems with it, you build careers on it. Everything is structured around rational, predictable outcomes. But what if I told you that the most complex piece of machinery you operate, your own brain, is running on some seriously buggy code? Yeah, even the most logical minds have systematic errors, and today we're going to debug them. All right, here's our game plan. Think of this as the user manual for your brain. First, we're going to bust the myth of perfect rationality. Then we'll look at the ideal decision-making blueprint versus our messy reality. After that, we'll debug some very common mental shortcuts, isolate a really dangerous bug I'm calling the overconfidence virus, and finally, give you a new cognitive toolkit to take with you. And this is really the core question here, isn't it? We're going to reframe these psychological quirks, these cognitive biases, in a language we all get, as predictable, systematic bugs in our mental operating system. And just like any good engineer, once we identify a bug, we can start to patch it. So let's kick things off by looking at the perfect algorithm, the ideal blueprint for making a decision. This is the logical process we all think we're following, especially when the stakes are high. Now, this is fascinating. This is the textbook model for perfect rationality. It's a completely logical step-by-step process. You design the problem, you weigh all your criteria perfectly, you generate every single alternative, rate each one, and then you compute the single best choice. It's beautiful, it's clean, and it's almost never how the human brain actually works. And here's why. In reality, our brain is running on two parallel operating systems. System 2, well, that's the engineer. It's the slow, deliberate, analytical thinking we just described. But we spend most of our lives running on System 1. That's our autopilot. It's fast, it's intuitive, it's super efficient, but it's also prone to making quick judgments that can be very, very wrong. And this solution shows you the problem perfectly. Just look at these two tables. Your gut, your System 1, is screaming that the table on the left is long and skinny, and the one on the right is short and wide. But I'm telling you, and seriously, pause and check with a ruler if you want, the two tabletops are physically identical in size and shape. Your own data will prove your intuition wrong. Even when your logical System 2 knows the truth, your intuitive System 1 refuses to see it. That's how powerful these bugs can be. So here's the thing. We aren't supercomputers. The economist Herbert Simon actually won a Nobel Prize for this idea of bounded rationality. All it means is that our ability to be perfectly logical is boxed in by real-world limits. We don't have all the information, our brains don't have infinite processing power, and, well, the project is due tomorrow. Now, to deal with these limits, our brain relies on mental shortcuts or heuristics. The best way to think of them is like efficient code libraries. They save a ton of time and energy, and you know what? They work perfectly like 95% of the time. But just like a popular open source library, they can have hidden bugs that cause systematic, predictable errors when you least expect it. On this slide, you see three of the most common ones. The availability heuristic, for instance, makes you overestimate the chance of a server crash just because you dealt with one yesterday. The representativeness heuristic can make you see a pattern in what are actually just random bugs. But today, we are going to debug the one that is, I would argue, the most dangerous for any analytical professional. Let's zoom in on the confirmation heuristic. We're going to call it the confirmation trap. It's our brain's default setting to look for information that proves we're right instead of searching for information that could prove we're wrong. To see this bug in action, let's run a quick diagnostic. Right now, I have a rule in my head that the sequence 2, 4, 6 follows. Your job is to figure out my rule. You can suggest any three-number sequence you want, and I'll just tell you if it fits the rule or doesn't fit the rule. So, what's the first sequence you'd test? If you're like most people, you probably thought of 8, 10, 12, and I'd say, yep, that fits the rule. Then you might try 100, 102, 104, and I'd say, yes, that fits too. So you'd confidently say the rule is add 2 to the previous number. And you'd be wrong. See the trap? You only tested sequences that confirmed your hypothesis. You never tried to break it. The actual rule was just any 3 ascending numbers. Now think about your own work. When you're testing a new design, are you running the tests you expect it to pass just to confirm how great it is? Or are you actively trying to break it? Are you testing the edge cases that would prove your design is flawed? The confirmation trap makes us lazy testers of our own ideas, and this bug gets supercharged by another one. And that brings us to the master bug, the one that acts like a rootkit, amplifying the damage of all the other biases we have, and that is overconfidence. It's the little voice that convinces us that our initial idea, our plan, our estimate is way better than it actually is. In the world of engineering, this virus usually shows up as the planning fallacy. It's our systematic, well-documented tendency to underestimate the time, the cost, and the risks of our projects, while at the same time overestimating the benefits. It's why almost every project plan is, let's be honest, a work of fiction from day one. A classic, and I mean catastrophic example, is Boston's Big Dig highway project. The initial plan was just wildly optimistic. It was based entirely on a best-case scenario view of the world, and it completely failed to account for the thousands of little things that could, and absolutely did, go wrong. The final cost was more than 5 times the original budget, and it finished 9 years late. This wasn't just a rounding error, it was a catastrophic failure of estimation, driven by that powerful 1-2 punch of overconfidence and the confirmation trap. They only looked for evidence that confirmed their optimistic view, and they failed to look for anything that might prove them wrong. So, how in the world do we start debugging this faulty code in our heads? Well, the source material, inspired by social psychologist Kurt Lewin, lays out a simple 3-phase process. It's all about creating a new, more robust mental workflow. First, you have to unfreeze your current habits. That just means accepting this one fundamental truth: you are vulnerable to these biases. I don't care how smart you are, this is hardware-level stuff. Step 2 is change, where you actively install new mental tools to fight back against the bugs. And finally, refreeze, where you practice these tools until they become your new default process, basically baked into your workflow like a unit test. Here are 3 practical tools you can install today. First, actively seek disconfirming evidence. This is the fix for that 2-4-6 puzzle. Make it a rule. For every 3 data points supporting your idea, find one that challenges it. Second, explicitly consider the opposite. Run a pre-mortem. Get your team in a room before a project starts and ask, okay, it's a year from now and this project failed spectacularly. What went wrong? This gives people permission to voice concerns. And finally, broaden your frame. Never estimate a project in a vacuum. Go find data on 5 similar projects and see how long they actually took. Use that real-world data as your baseline, not your gut feeling. So let's bring it all home. Look, understanding these biases isn't just some neat psychological trick. It's about applying the same rigor, the same debugging process you use on your code to the most important system you will ever operate, your own mind. The first step to writing better mental code isn't about being smarter. It's about being aware of the bugs. So, what's the first one you're going to go fix?